Hi everyone, welcome back to this tutorial. In this video, we can discuss about the 2's complement representation of signed numbers. In our previous videos, we have discussed about the 1's complement as well as signed magnitude representation of signed numbers. Okay, so how to get the 2's complement representation of a binary number? To get the 2's complement representation, simply invert the given number and add 1 to the least significant bit of the obtained result. This is the rule to get the 2's complement form. Okay, what is it? Convert the given binary number to its 1's complemented form first. Then add a single 1 to it. Consider one example. This is the given number. We need to get the 2's complement form of it. To that, what we want to do, get the 1's complemented form of the given number first. How to get the 1's complemented form? Simply invert each and every bits of the given number. If it is 0, take as 1. If it is 1, put a 0 there. Okay, so this 0 become 1 here. These three 1 become zeros here, and this 0 again 1. This one as 0, and this 0 as 1 and this 1 as 0. So this is the 1's complemented form of given binary number. Then in order to get the 2's complemented form of it, add a simple 1 to it. Okay, so while adding this is the result. 1 plus 1 is 0, carry 1. That carry 1 is added with this 0 and get this result. Okay, so this is the 2's complemented form of given number. Next, so these are certain binary numbers. So in 2's complemented form, this is actually 0. This is positive 1, positive 2, positive 3, positive 4, positive 5, positive 6 and positive 7. 4-bit representation. Okay, so positive numbers are represented in its binary form with sign as 0. This is the same both in 1's complemented form, 2's complemented form, also in signed magnitude form. The positive numbers are represented in a similar way in signed magnitude form, 1's complemented form, 2's complemented form with sign bit. The M must be bit as 0. But the negative, corresponding negative numbers are represented with different pattern. Okay, in sign magnitude form, for the negative numbers, the MSB bit is always 1 and remaining bits indicate the magnitude. Okay, so and in 1's complemented form, to get the negative of a binary number, just take the inverted form of each and every bit of the given number. Okay, so here, suppose these are the positive numbers represented in 2's complemented form. Okay, now we need to get the negative of these in 2's complemented form. For that, takes the 1's complemented form of it first, then add a single 1 to it. So, take this table. This is actually calculated in our previous video. Okay, so this is actually negative 0. Right? 1's complemented form of it is 1, 1, 1, 1. So, in order to get the 2's complemented form, what we want to do? We want to add a 1 with this 1's complemented form of it. So, while adding 1 plus 1 is 0, carry 1. The carry is added with this 1. Again 0. With carry 1, 1 plus 1, 0, carry 1, 0. And here we have an end carry. So, in 2's complemented form, if this arithmetics generate an end carry, simply drop that end carry. Okay, we can discuss about this arithmetics in detail sometimes later. So, here we need to discard that carry and the remaining bits form the 2's complemented representation of this given binary number. So, here the zeros. For both positive 0 and negative 0, the representation is the same. This is an important point regarding this 2's complementary representation. That is, for 0, we have only a single representation. That means no ambiguity in case of 0. Ambiguity exists in case of 0 in 1's complementary representation as well as in sign magnitude representation, because there exists negative 0, a particular representation for negative 0 and another representation for positive 0. 0 is normally considered as neither negative nor positive. So the condition is satisfied in case of 2's complementary representation. We have only a single representation for 0. This 0 is not considered either as positive or negative here. So no ambiguity in case of 0 here in 2's complementary representation. This is an important point regarding this 2's complementary representation. Now we can take the 2's complement representation of 1, positive 1, that indicate actually -1. What is it? For that, take this binary and its 1's complemented form, that is this 1 1 1 0. Actually, we don't want this table. We can directly get the 1's complemented from this binary representation of this positive 1. That is, this 1 is inverted, that is 0, and remaining 3 get inverted to form 1 1 1 0. To that, we need to add 1 in order to get the 2's complemented form, that is 1 1 1 1. So this is the 2's complemented form. Okay, after converting this, or after getting the 2's complemented form of this binary, we get this 1 1 1 1. This is actually -1. Okay, now we need to get the representation of -2 in 2's complemented form. So for that, what we want to do, take the representation of positive 2 in 2's complemented form, then take its 2's complemented. Okay, so for that, first get the 1's complemented form, then add a single 1 to it. Okay, so while adding 1 to the 1's complemented form of this, we get 1 plus 1 is 0, carry 1, that carry 1 is added with this 0, that is 1, and put these 1 directly down here. So 1 1 1 0 is actually -2. This is actually the 2's complement of positive 2. Okay, and similarly, the 1's complement of this representation plus 1 is this 1 1 0 1. This is actually -3 in value. Okay, and thus for 4, the 2's complement is 1 1 0 0. This is actually -4. And similarly, others are also listed here. Okay, so this is the normal method for getting the 2's complement of a given number. What is it? Take the 1's complement of the given number, then add a single 1 to it. Then we get the 2's complemented form of it. If the given number is negative, then while taking the 2's complement, then that becomes its positive corresponding number. Okay, now I am going to teach you a simple method to get the 2's complement of a given number directly. It will help you to solve certain problems in GATE exam and some competitive exams. Okay, so consider this is the given number and you are asked to find the 2's complement of it. Usually what we want to do, we want to take the 1's complement of it, then add a 1 to it, right? But here we have a direct method to get the 2's complement, that is scan from the right hand and proceed towards left. And if a 1 is obtained for the first time, stop there. And remaining bits we want to invert. For in this particular case, start the scanning from right hand and proceed towards left. Here this 1 present in the first position, the LSB bit position itself. So stop directly there and invert the remaining bits. This is our first one, which is present in the first position itself. So stop there right now and invert the remaining bits. The 0 become 1, this 1 become 0 and this 0 become 1. So this is the 2's complement. Is it the right answer? Check for it. Actually, this is the given number. This is actually the 2's complement or the binary representation of this. 0, 1, 0, 1 is positive 5 actually. Okay. Then, after converting, that means start from the right end, stop there and invert the remaining bit. This 0 become 1, this 1 becomes 0 and 0 become 1. That is the representation for minus 5 in 2's complement form. 1, 0, 1, 1. Okay, so we can use this method in order to solve the problem in a faster way. So another example. This is actually minus 6. The 2's complement form of minus 6. Right? So start from scanning from the right end and proceed towards left. So in the first position it is 0. So proceed to next bit position. Here it is 1. So stop there right now. Then up to that point, from the right end and up to the first one, keep the bit as it is. Then after that, towards the left, invert the remaining bits. That means this is the first one present while scanning from right end towards the left. Stop right now here and these bits are kept as it is and invert the remaining bit after this 1. This 0 become 1, this 1 become 0. This is the 2's complement of given number. The given number is actually 1010 in, that is minus 6. So its 2's complement is this. Okay, so this is the method for getting the 2's complement of a given number in a direct or simple way. From this example, it is clear that the 2's complement of positive 6 is 6. 2's complement of positive 6 is minus 6 and the 2's complement of minus 6 is positive 6. This is valid for all the numbers. Okay, this is a common question you can expect for your competitive exams. Suppose 2's complemented form of a given binary number x is y. Then 2's complement of y is what? What is it? The answer is x itself. That means the 2's complement of a 2's complemented form is the number itself. 2's complement of x is 2's complement of positive 6 is minus 6. Again take the 2's complement of it. That is the number itself. So the answer is x itself. Okay. So here these are the numbers that we have evaluated in our previous example or previous slide. Okay, so these are the numbers that we can represent in 2's complemented form using 4 bits. Here we have positive numbers as well as negative numbers. And the main advantage here is no ambiguity in case of 0. Okay, using 4-bit total we have 2 to the power 4, 16 different combinations are possible. And here no ambiguity in case of 0. So this particular combination is not yet used here. Right? All other combinations are used or derived for different positive and negative numbers, but this one is not yet used anywhere here. Okay, so this particular, what is the value of this particular binary representation in 2's complemented form? What is the value of it? How to get the value of a binary number? To get the value for the unsigned number, we know that to get the value or the decimal equivalent, value is actually the decimal equivalent, right? So to get the value, we need to find out the positional weightage of each and every bit of the given binary number. So in case of unsigned number, that means in case of positive numbers only, we need to consider the positional value like this: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, up to 2 to the power n minus 1 in case of n bit binary number. Here we have only 4 bits. So 4 positions are needed. Okay, this is the case of unsigned numbers. So how to get the value of this particular binary number? 0 into 2 to the power 0 plus 0 into 2 to the power 1 plus 0 into 2 square plus 0 into 2 cube. So while adding all these product terms, we get the value 0. But in case of 2's complemented representation, the positional weightage is different. In signed numbers, actually, this 2's complement numbers, 1's complement numbers, and signed magnitude numbers are used for representing both positive and negative numbers, right? So the positional weightage is different here. The weightage is like this. In case of 4-bit representation, we can represent the positional weightage like 2 to the power 0, 2 to the power 1, 2 square, and minus of 2 cube. Why? Because we can represent positive and negative numbers here. Okay, so the last bit, in case of n-bit representation, the positional weightages are like 2 to the power 0, 2 to the power 1, 2 square, 2 cube, etc. up to minus 2 to the power n minus 1. So in this case, in case of 2's complemented form, we need to represent the positional weightage like this in case of 4-bit representation. So in this, the value is 0 into 2 to the power 0 plus 0 into 2 to the power 1 plus 0 into 2 square plus 0 into minus 2 cube. Here all the product values are 0. So the final result or the final value is also 0. Consider another example. Suppose this is the number represented in 2's complemented form, and thus 1 into 2 to the power 0 plus all the other 3 products are 0 because all these bits are 0. So 1 into 2 to the power 0, 2 to the power 0 is 1 itself. 1 into 1 is 1. Right? So this is actually the value of this binary representation is actually positive 1. Next example. Here 1 into 2 to the power 0. 2 to the power 0 is 1. 2 to the power 1 is 2. 2 square is 4. Minus 2 cube is minus 8. Okay. So 1 into 1 plus 1 into 2 plus 1 into 4 plus here 0 into minus 8 is 0. 0 plus 4 plus 2 plus 1 is 7. This is positive 7. The value of this binary number in 2's complemented form is positive 7. Another example, here 1 into 1 plus 1 into 2 plus 1 into 4 plus 1 into minus 8. That is minus 8 plus 4 plus 2 plus 1. Minus 8 plus 4 is minus 4. Minus 4 plus 2 is minus 2. Minus 2 plus 1 is minus 1. Right? So, this is the value of this particular binary representation in 2's complemented form. This is for this particular 2's complement representation, the value is actually minus 1. Okay, consider another example. Here, these two terms, the product terms corresponding to these two bits become 0. So, 1 into 1 plus 1 into minus 8. That is minus 8 plus 0 plus 0 plus 1. That is minus 7. For this particular representation, value is actually minus 7. Okay, for this particular binary representation, what is the value? These three product term corresponding to these 3 bits become 0. So, minus 8 plus 0 plus 0 plus 0 is minus 8. So, this particular representation in 2's complement form is actually minus 8. Okay. Now, we can consider the range of numbers possible in 4-bit using 4-bit in 2's complement representation. We can start from minus 8 up to 0, then up to positive 7. So the range of numbers in 2's complement form using 4-bit is minus 8 to positive 7. Okay, so here the main advantage is in our previous cases in 1's complemented form and signed magnitude form using 4-bit, the range of values is from minus 7 to positive 7 because there we have an ambiguity in case of 0. That is, we have representation, separate representation for 0 in positive and negative terms. But here we have only a single representation for 0 in 2's complemented form. That is why we can add one more negative numbers, or we can represent one more negative number. That is this minus 8, and the values ranging from minus 8 to plus 7. This is the second advantage of this 2's complemented representation. We can represent more number rather than this 1's complement and signed magnitude representation. So usually our digital system preferring this 2's complement representation for storing our signed numbers. Okay, so we can now write a generalized form for representing the range of numbers possible in case of n-bit representation in 2's complement form. That is this. Minus of 2 raised to n minus 1 to plus 2 raised to n minus 1 minus 1. Is it correct? Check for that. Substitute 4 for this n, that is n equal to 4. In that case, this n become 4. 2 to the power 4 minus 1 is 2 to the power 3. Minus of 2 to the power 3 is minus 8. Minus 8 to plus 2 to the power 4 minus 1 minus 1 plus 2 to the power 3 minus 1, that is 2 to the power 8. 2 to the power 3 minus 1 is 8 minus 1, that is positive 7. Minus 8 to positive 7. We can represent more numbers using n-bit in case of 2's complement representation rather than our 1's complement and signed magnitude representation. This is the second advantage of this 2's complement representation over the other two. Okay. So this is some additional information that is discussing with you. This will help you in your competitive type exams. Okay, if you are interested, we can go through this. Okay, in case of 1's complemented representation, how to get the value of a given binary number in 1's complemented form. This is the method for getting the value of a given number in 1's complemented form. In order to get the value of a given number in 2's complemented form, we need to consider the positional weightage like this. Right? The MSB bit is given with the negative sign. This is actually based on this range value. Okay. In 1's complemented representation, the range is actually like minus of 2 to the power n minus 1 minus 1 to plus 2 to the power n minus 1 minus 1. Okay. Based on that, we can represent the positional weightage in case of 4-bit representation like this. 2 to the power 0, 2 to the power 1, 2 square and minus of 2 to the power 3 minus 1. That is minus of 2 to the power 4 minus 1 minus 1. Right? This minus is actually used here because here we need to consider the sign of the given number also. Why? Because the 1's complement and 2's complemented representation are used for representing both signed and both positive and negative numbers. Okay, in order to distinguish between them or in order to identify the positive and negative numbers properly, we need to consider the sign of the given number also, given binary representation also. Okay, so here the weightage is like this. In case of an n-bit binary number in its ones complement representation, the positional weightages like this: 2 to the power 0, 2 to the power 1, 2 square, 2 cube, etc. up to minus of 2 to the power n minus 1 minus 1. Okay, so here we are considering 4-bit representation in ones complemented form. So here for positive 0, the representation, binary representation in ones complement form is like this, and its value is obtained while considering the positional weightage. 0 into 2 to the power 0 plus 0 into 2 to the power 1 plus 0 into 2 square plus 0 into minus of 2 cube minus 1. Minus of 2 cube minus 1 is minus 7 actually. Here all the bits are 0. So 0 plus 0 plus 0 plus 0 is 0 itself. Here the value is actually 0. Whether it is positive 0 or negative 0 in one's complemented representation, its value is 0 only. Okay. Next example 1 0 1 0. So here 0 into 1 plus 1 into 2 plus 0 into 4 plus 1 into minus 7. Okay, only these two terms become 1 and the other two product terms are 0. So minus 7 plus 2 is minus 5. For this particular representation, its value is actually minus 5 in one's complemented form. And next, for this particular representation, this is 1 into minus 7 plus 0 plus 0 plus 1 into 1. Minus 7 plus 1 is minus 6. Okay, and for this, 1 into minus 7 plus 1 into 4 plus 1 into 2 plus 1 into 1. Minus 7 plus 4 plus 2 plus 1 is actually 0. So this is actually a mistake. Here we don't want to put this negative sign here. Whether it is positive 0 representation or negative 0 representation in one's complement form, its value is 0 only. Okay, so we don't want to put this negative sign here. The value is 0. Okay, minus 7 plus 7 is equal to 0. That is the value of this particular representation. Here also the value is 0. Right? And in this case, this is 1 into 1 plus 1 into 2 plus 1 into 4 plus 0 into minus 7. That is 4 plus 2 plus 1 is 7. For this particular representation in one's complement form, its value is 7. And for this representation, this is 0 plus 4 plus 2 plus 0. That is 4 plus 2 is 6. Positive 6. So for this particular representation in one's complement form, the value is positive 6 actually. This is the case of one's complemented form. If your number is given in one's complement form and you are asked to find its value, so we can consider the positional weightage like this in one's complemented form and this in two's complemented form. This is based on our range values. But in case of sign magnitude representation, we don't want to consider these ranges. In sign magnitude form, the MSB bit actually indicate the sign value. Okay, so the method for evaluating the value of a binary number in sign magnitude form is first check the sign bit or the MSB bit. Whether it is 0, that means it indicates a positive number. Okay, so after fixing the sign, then consider the remaining bits and consider this as an unsigned number and evaluate its magnitude. That is 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 square. Right? This 0 actually used for indicating the sign. It is 0, that means this is positive number. And using the remaining bit and treat this remaining bits as unsigned numbers. So 0 plus 2 plus 1 is 3. Consider one more example. Here, first consider this sign bit. Here it is 1. That means the given number is a negative number. So, put a negative sign here. Then treat the remaining bits as unsigned numbers and evaluate its value. 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 square. Right? That is 0 plus 2 plus 1, that is 3. Magnitude is 3. But the sign is negative. Because sign bit is here, it is 1. 1 means this is a negative number in sign magnitude form. Okay, we have already discussed the representation of 1's complemented, 2's complemented and sign magnitude form of signed numbers. Okay, and in our next video, we can discuss in detail about the arithmetics in 2's complemented form. Thank you.